Good afternoon. We're about to begin the program during lunch. You know, as we uncover the individual differences and vulnerabilities in risk and the underlying mechanisms and utilization of individualized countermeasures, space medicine stands to gain enormously from the current era of omics and personalized medicine. And to help us better understand exciting new discoveries in this field, we're very fortunate to have as our luncheon speaker today Dr. Richard Gibbs. So Richard holds the Wilford Kane Chair and is professor of molecular and human genetics at Baylor College of Medicine. He's also the founder and director of the Human Genome Sequencing Center at Baylor. And his group was one of the 5 worldwide sites to undertake and complete the Human Genome Project, culminating in contribution of approximately 10% of the sequence in 2003. And his research continues to be at the forefront of developing new technologies and instrumentation, making important discoveries in mapping and sequencing, exploring novel chemistries for DNA tagging, advancing bioinformatics, and making other significant contributions. And he's received many prestigious awards for his work. And Dr. Gibbs is a member of the Institute of Medicine of the National Academies. It's really a pleasure as a colleague and a friend to welcome Richard to deliver his talk.
Thanks to Dr. Sutton and Dr. Alford and Mr. Abbey for having me come to meet with you. I'm kind of nervous giving this talk, I've got to tell you. You're from a community that's outside of the biology community I normally work with, and yet we have many similarities. I was reflecting at breakfast how we went for many years in the Genome Project telling everybody this is our moonshot. And that's perhaps a little bit of hubris. I certainly didn't take some of the risks and some of the uncertainties of the Moon program, but we did have some similarities. And I also somewhat immodestly would go on to say, I do hope that one day some of you are saying, when you do your next venture, this is our Human Genome Project. We'll see if that eventuates. So what I really want to talk to you about in my brief comments here, it can all be summarized under the general title of genetic determinism. Genetic determinism at its simplest is the idea that the gene makes the person, or the combination of genes makes the complexity of the person, and that you can draw a direct lineage from the gene knowledge to the state of the person, and you can use that somehow productively. This has some negativities as well. It's the idea that a certain genetic complement might lead a person to be a certain way that they may not want to be. And there's much debate about the merits of genetic determinism. But fortunately, much of what we can say about genetic determinism is indeed rooted in science. I'm sure you've seen the Gattaca movie that's actually about space flight, where the individual is blessed or not as to be able to participate in space flight based upon their genetic sequence, and the theme of the movie is that someone evades that possibility by sneakily giving their wrong sample. I think those of us who are hardcore geneticists would subscribe to the notion that indeed there will come a time when a sequence of a person, a DNA sequence, is a determinant, perhaps certainly not the only one, but a major determinant of their suitability for any adventurous program like this. And I've put the picture on the right because we're often asked to contextualize this question of determinism in the context of human disease. And the way we phrase that is we ask people, what fraction of what is going to kill you eventually, because something will, do you think is genetic? And when we do that kind of survey, many people who are outside of the field of genetics say, well, it's kind of a small fraction because we know about those lethal childhood diseases that get people and everything else is adult. But if you go into medical biology, you know more and more there's a familial pattern to heart disease, to cancer, to schizophrenia, to congestive failure, whatever. And we can actually measure that heritability, and we can say that more and more is genetic. Some say everything that will eventually get you is genetic, except perhaps trauma. What if you get hit by a bus? You can't say that's genetic, and the picture on the right illustrates this awareness suddenly that the thickness of your skull is actually a big factor in determining how you deal with trauma. So indeed, even with trauma, there may be genetic factors. So, as geneticists, we've sort of departed from soft quantitative genetics now into a more hard form of molecular genetics through the study of DNA. And forgive me for putting in elemental slides about DNA. I'm sure most of you know this, but the facts are we each have about 6 billion letters in each of our cells that are our genetic code, and that's an enormous amount of data to measure, and was not known about that until 20 years ago. The DNA is organised into chromosomes, and the simplicity of genetics is that each of your parents has 2 copies of their genome. That's 6 billion, that's 3 billion for representing each copy, and that when a child is born, 3 billion letters, 1 copy of each genome is donated from each parent, reassorted into the child. The child again has 2 copies of the genome. Now, I often like to show this slide because genetics seems impenetrable to non-scientists, and this, I think, displays beautifully the simplicity of it. This is about 20% of the story of genetics. The next 20% is simply that DNA, if everything was always the same, genetics would be pretty dull, and that would simply be the way of passing on the code from generation to generation. Unfortunately, of course, there are new mutations each generation. And there's about a couple of hundred of those in each individual with each generation. And because the genes are about 1%, that means there's about 1 change in 1 gene in every individual, just by the virtue of the random mutagenesis process that happens in every generation. Now, as a consequence of that, we're all a little different. And because many of those mutations occurred in much prior generations and had a chance to radiate out, many of us share differences, many of us have differences that are unique to us. And that's the pattern, that's the mystery of human population genetics. Now, through the development of the Human Genome Project and other molecular methods, we've become to use the words genetics and genomics somewhat interchangeably. And I'll do that in my comments today. So basically what we mean now by molecular genetics practiced through genomics is that you can compare 2 genomes, and if you know the differences, and in the simplest case it's just 1 letter difference, and you know what that does to the attendant individual at the high-level phenotype, you've really done genetics. You've looked at the effect of a single change in the genome on what the individual is, and that's genetics. And it was the Human Genome Project that really allowed us to make this transformation. Listening to the talks this morning, I reflected on one fact, which is that in the Human Genome Project early on, we made a practical decision to share our data very widely. And right, even now, as soon as we generate data in any of the genome centres, it gets put onto the internet, it gets put onto the web, so it's freely available without any restriction at all. And I hope that I'll be happy to talk to any of you about the impact of that on our progression as a community, but I think it's certainly relevant to the data sharing comments this morning. So now we have the Genome Project behind us, and we can tackle some of these questions in genetics. Which kinds of genetics problems can we solve? Well, putting it simply, the easy ones we can solve, and the hard ones are really very hard and are very hard to solve. So what are the easy ones? The easy ones are represented by that bimodal distribution on the right, where you clearly have differential outcomes of different genotypes. You have a DNA letter change, you get a dramatic difference in the individual. You don't have the change, you don't get the dramatic difference. This is the case in the childhood diseases like cystic fibrosis, muscular dystrophy that many of you are familiar of. And of course, it's also true with some more exotic things, but also things that have simple genetics like sudden death heart failure due to ion channel mutations that are particularly relevant to things like sending people off into space. Now, at the other end of the disease spectrum, these complicated phenotypes, you see the continuous distributions. These are things like blood pressure, the behavioural factors. If you could quantitate different behavioural elements, you'll find they often have a broad distribution, height, and other physiological measures that relate to disease. These are believed to have many different genes contributing to the phenotype, which makes them hard to study. Examples here are adult heart of disease with these kind of distributions are adult heart disease, schizophrenia, and different response to low oxygen tension. And we had a mention today about skeletal osteoporosis, that kind of thing. All of those are in this hard category. Now, within human genetics, we formalise this a little more, and we broadly divide things into what we call the Mendelian camp and the common disease camp. So the Mendelian camp is that collection of childhood diseases, mostly childhood diseases, that result from single gene defects. And there are about 20,000 human genes. We know now about 4,000 of those genes linked to childhood disease. If you have a break in one of those genes, you have a childhood disease. And we've studied those and gained insight into gene function through those. On the common disease end, the diseases I mentioned before, heart disease and schizophrenia, we have large programs of examining thousands of individuals by genetic methods, but by and large we haven't been able to eke out too many of the precise nuts and bolts of those disorders, even though we have a lot of evidence of genome signals and genetic signals that broadly point to those diseases. So the upshot of this right now is that if you go into your doctor with a child with an inherited disease, with some problem that looks like it's a genetic disease, you've got a good chance of resolution. If you go in as an adult with your DNA sequence, and the doctor is obliged to look up the data on all of the DNA sequence in the adult onset disorders, it's very unlikely that you'll get information that's actually useful for you as an adult. That's the state of the art, and that's what we aim to fix through studying genetics. Now, the study of genetics, of course, is proceeding like most good studies do as it now becomes more formal and more comprehensive, with a layer of description, complete cataloguing, a layer of understanding before we can hope to manipulate it. So our description really is that Human Genome Project phase and the analysis then of the basic function of all genes. And we're moving from that now into this next phase of understanding how all the genes work together to building processes, so eventually we can build therapies and manipulate those. Of course, we want to do more than just understand basic, how the watch parts work. We want to apply our process understanding and our biological systems manipulation to real health problems, which is the field of genomic medicine. So here is a fairly Houston-centric, I would say, map of the progress through this journey of description, understanding, and bringing this understanding into practice in a way that actually influences people. At the top there is the Human Genome Project, which finished in 2003. And after that, as the technologies evolved, we went through a series of individual human genome projects. And the idea here was that instead of doing a mosaic, little parts of half of a genome, which the Human Genome Project represented, we used that reference information from that project to take single individuals, take all of their DNA, get complete sequence, and then map that sequence back to the reference and figure out what we meant for it. We first did a project with James Watson. It was a project between Baylor and a company called 454, and he was the sort of archetypal first human complete sequence. We did a project I won't talk about with Desmond Tutu. And then we did a series of individuals with Jim Lupsky and then the Beery twins and then an anonymous person there, which represented progression through obtaining sequence to understand information, through obtaining sequence to guide clinical activity, and then back to driving discovery so we can fill out this full model of complete understanding and understanding how all human genetics works. So I'm not going to say anything really about technologies today. Jeff Sutton, I hope you didn't expect me to show a whole lot of DNA sequencing machines and molecular tools and all of that. You can just be confident that all that's evolving. But the bottom lines here are that the evolution has been incredible. We've gone from a $3 billion half genome to about $5,000 complete genome, which is supposed to be a $1,000 genome right now, but it never works out that way. We've also developed methods in the last 5 years where we don't look at whole genomes, but we just pull out the genic portions. So, genes are arranged through the genome in individual parts that are stitched together. Those parts are called exons. We have oligonucleotide techniques now that can pull the exons out of a sample and allow you just to use your sequencing for the genic portions, bringing the cost right now down to about $700 for the analysis of all the genic portions of one genome. And the third part here is we've developed these massive data handling and management capabilities. And here's a slide that illustrates a recent poster child experiment we did where we took the information from over 10,000 different genomes and piped it up into the cloud, did primary computing on analysing all the variants in those genomes, and then distributed the data to a network of 50 different collaborative groups. And we won the prize for the biggest compute at Amazon. That was our good news. So we've got massive data handling and computational capabilities developed. So these things have been happening in parallel as we've done these demonstration projects. As we did the demonstration projects, we learnt new things about biology. All the way back before we did the Watson project, if you'd gone to a geneticist and said, how uniquely different are we in our genic portions? The answers pretty much were maybe 10 to 100 unique things to you, unique changes amongst your genes. After we sequenced Watson, and here he is getting a genetic counselling from my colleague, Jim Lupsky, and being told that your DNA looks fine. That's all we knew to tell him at that stage. After we looked at Watson and compared his data to the databases and to the contemporaneous Craig Ventnor sequence, we were able to realise there was much more private variation. And the short version of that long story is that from that work and other population genetics inference work, we then realised that if you sequenced everybody, for example, in this room, the first person we sequenced would have 300 to 500 unique genetic differences in them. So would the second, so would the third, so would the fourth, all the way through the room. It's not as if, as we accumulate all this sequence, we're seeing every change again. In fact, the nature of new changes that it's accumulating keeps going on and on. The curve now, with hundreds of thousands of genomes out there, is just beginning to taper off. So this is the message. We each have a lot more private genetic variation than we thought. Now, we went on from there to actually sequence Jim Lupski, and he has a genetic disease, and this is called Charcot-Marie-Tooth syndrome. It's a peripheral neuropathy. And it can be quite severe. Jim is reasonably severely affected, and he has family members affected. Jim is actually an expert on that disease, having discovered many of the causes. Now, the short story about this disease is that 20 years ago, it was thought of as a single syndrome with some clinical heterogeneity. And through Jim's work, primarily, it was discovered that a single genomic change described about 60% of the familial cases, but in addition to that, there are as many as 40, now known to be 40 other genes that can individually cause the disease. So the clinical picture is now described molecularly as a heterogeneous collection of disorders that form this one syndrome. So Jim had found that major cause for most people, had never found the one in the family. We took these new sequencing methods and bled him, and in a month, for about $50,000, we found the gene in him that causes his disease. That was a dramatic demonstration of how the sequencing methods can rapidly lead us to discovery. And the third vignette I'll show you here involves some children who came along to us shortly after that, who were quite normal at birth, but then rapidly got worse. They developed many symptoms. They regressed. They were then diagnosed in a strange way with having cerebral palsy. Now, the mother was very astute and recognised they may have a dopamine responsive condition, and actually with her neurologist tried dopamine and restored much of their health until their teens, when they began to regress again when we saw them. At that stage, one had very bad breathing issues, nearly died several times in the night. The other one had shaking and drooling. They were really in bad shape. And the short story here is that we sequenced them, and we were able to recognise that the genetic lesion was in a cofactor not just for the dopamine responsive pathway, but also to the serotonin responsive pathway. So a simple supplement restored their health very quickly. So they're now a dramatic poster child for the use of sequencing in medicine. Now, these methods and our successes has spurred a number of cottage industry discoveries in gene genetics so that we can improve the depth of this catalogue of known defects associated with human genes. As I said, there are 20,000 genes. There are at least 10,000 of those that we should be able to find a child with a disease that is caused by a defect in one of those genes, and there's perhaps all 20,000 can eventually be found. So we've been working way to do that, and in fact we've somewhat industrialised that process and built a worldwide network of collaborators that do that. And here you see a map in the bottom right-hand side of the slide that shows many countries inputting samples into a research effort that aims to increase the discovery of these Mendelian genes to help build up this catalogue. Now, by contemporary standards, this is going very well, and in the last 2 years, the network has discovered about 300 new genes to add to this catalogue. But the problem is that this is still too slow, and each one of those discoveries that I'm making sound very straightforward is quite a burden on its own. So we've been looking for a paradigm shift to more rapidly guide this work and to help feed back into our whole discovery process to build our knowledge of genetics and ultimately our networks and how we all fit together genetically. As part of this program, we opened a clinical lab about 2.5 years ago across the road here. It built in the new methods, and it offered to do sequencing of children for clinical purposes, not just for research purposes. And that laboratory has grown in its activity over this 2 years, so we see about 200 cases a month. The insurance companies pay for all of these 200 cases, so we're seeing 200 cases get their families sequenced. Now, if the insurance companies would pay for all cases that came, they're denying about half right now. We could probably double that volume tomorrow. So the result is we have now a steady flow of patients that, not that we have to drive around to find to see who might be good to study for a genetic disease, but patients who are coming to the front door to ask for clinical service to see if they have a known gene mutation. And if they don't, they then become available for research, because we might discover new genes in them because their gene mutation was not in the Mendelian catalogue. We can then ask them to participate so we can use them to grow the Mendelian catalogue. Now, this is a very laborious process right now, and you see a lot of humans here sitting around. These are the people who look at the data as it comes through, and it's a very manual process, and I won't take time today to tell you about the automatable parts of it, but this is what we do on our day-to-day basis, sitting around looking at these kind of data. The patients get a report that says, here's your critical mutation. They also get a report saying, here's your variants of unknown significance. We think they might be important, we're not sure. And if they want, they can also get a report that says, here are your incidental findings. That is, here are findings which might be cause cancer in the family or something like that. Now, here's my genome. I put my genome through the clinic through a program that Dr. Kasky here designed. And I can tell you that this is one more reason why I never could be an astronaut. I carry 2 mutations. My mother had Waardenburg syndrome, which is a deafness syndrome, and heterochromia, different coloured eyes, and some kidney issues, and I was concerned I might have that allele. I don't, but I do have a carrier condition in 2 genes which have, in some cases, in some families, the carrier state does have problems with vision and problems with hearing, and I do have some edge hearing problems. So I would say if I was amongst a list of candidates with their sequence, and I was the guy with a couple of carrier mutations in these loci, I might get pushed to the bottom of the list. Whether that ultimately affects my health as it unfolds, I think we've really got to fully understand. So this engine now of people coming to the clinic is a huge, it's beginning to substitute for our research mode of collection for discovery. And we're finding things like, you see on the bottom left here, a list of patients that actually turn out to have 2 different heritable diseases. So they had symptoms and a clinical picture that couldn't be properly articulated and understood, but when you look at the molecular data, you see 2 different genes. Each gene has a known set of symptoms, and when you look at the aggregate patient, they've got the combined set. And other ancillary research discoveries I won't belabor right now because we're going quickly. So this sounds terrific. We're solving genetics. We've got people coming to our door for genetic treatment. The insurance companies are paying for them to be pre-screened, and then we're moving them over into research to find the things out that we don't know. It's not quite as smooth as I make it sound. This barrier that's illustrated on this slide of the HIPAA rules, which appropriately divided people into patients or research subjects, makes it quite arduous to get the patient material over into the research arena, but that is a struggle that we're dealing with well, and we're beginning to get a proper flow there. Now, the result is a larger number of discoveries and an accelerating rate of discovery, and I'll just briefly tell you one instance of that. When we had a referral of a colleague who said their child had a dreadful disorder and actually died at age 6 months, and gave us the sequence of the child. We could not properly interpret what was going on in that family, but when we asked our colleagues around the world and looked in our own database, we found an additional 3 cases that would never have been linked clinically to the first one, but through the molecular data told us that the same gene was burdened with a new mutation. And in retrospect, after that, when we went back and revisited all the clinical notes and revisited the clinicians, we were able to convince everybody this was indeed the same syndrome. So we now have a new syndrome based upon that gene's mutations that joins together those patients. And now we're seeing worldwide a streaming in of additional patients with those disorders. So the enterprise is working very well. So now if we go back to our sort of grand vision here of somehow we're going to use genetics, we'll know so much about genetics that we can read a sequence and predict what a person is. And I've told you that on the left here there's the acronym GWAS. This is the large-scale common gene survey methods that hasn't found a lot of information that you could use if you went into your doctor or wanted to predict your suitability for spaceflight, the military, or teaching, or anything else. And in the middle there, I've shown the Mendelian cases that I've just shown you the many examples of new discovery that's getting better and better and easier. You might reasonably ask, that's great, but how do we join these things together How do we take all this Mendelian data, these single gene defects, and explain the complex common GWAS disease? And we say that you can do that through what we call the understanding of oligogenic interactions, the bottom-up model building of a few genes interacting to together describe a phenotype. And so my last set of slides here will show you an example of how that's actually working, that our methods are precise and accurate enough, that the numbers are large enough, and that we're moving in that direction. And again, it's back on that Charcot-Marie-Tooth disease that Jim Lupsky has, that he was diagnosed with and for which we found the exact gene in his family. There are many, many cases of that disease for which the genetic etiology is not known. But now, when we go back and look in some of those cases, and we ask what's going on in those individuals, and we did this in a set of about 40 people just recently, we find a few cases that were actually missed in the primary diagnosis, known genes that should have been found. But in many of the remaining patients, what we find is not single genes that are so badly damaged that we have a clear Mendelian disease effect, but we find carrier states in multiple genes. So it's a subtle contribution of many of the contributing loci, each slightly damaged, that together is building the phenotype. Now, how do we know that? We do statistical comparison of the Charcot-Marie-Tooth cohort, and we do a control group. We do not yet have enough data to do this naively with the whole genome's worth of data. But if we constrain it to the 400 genes out of 20,000 that are ever known to be involved in neuropathies, we have a statistically significant signal. The Charcot-Marie-Tooth group with the non-simple case genetics has a burden in those genes that is significantly greater than any control group. And if we map that out, it actually looks like this, because many of those genes are involved in mitochondrial function. So there's a nerve, a long axon depicted in the top there, and a close-up of a mitochondria. And if you see the legend on the left, each circle represents a gene that's known to be in this series. The filled-in circles are the genes with mutations that clearly on their own can cause the disease, simple Mendelianizable forms, but all of the open circles are the genes for which a carrier burden state is added. And we see this accumulation of those open circle genes in particular individuals. So the bottom line is a person will come in with the problem. We might never find a gene that is completely dysfunctional in that individual, but we'll find 4 or 5 which each have partial damage. So our task now is to build those oligogenic stories to ground up reconstitute human disease genetics. And we're seeing success here in the neuropathies. There's also similar work going on in muscle function, in the alimentary canal, in skeletal disorders, and in other syndromic conditions. And this is the beginnings of building up a whole complete story of human genetics. So that's my conclusions from my comments here. I do want to go on and point out how this is going to change, just 2 more slides, to change somewhat the way we're thinking and the way we're doing business or doing our science in genetics, and that this is going to have a huge impact on us. And I like to couch this under the title of armchair futurism. So what's armchair futurism? How is it different to just saying what's going to happen? Pretty much, if you go around and ask people what's going to happen in genetics, what impact it's going to be, they tell you about insurance problems, privacy concerns, some health benefits, fairly linear things that go on in the future. But we all know that the future changes in dramatic and uncertain ways. And the best examples, of course, are the classic, who would ever need more than 64 kilobytes of memory in a computer? Or who would need a cell phone? Or what's the internet going to do for us? And this kind of dramatic shift, I think, is happening right now for us in genetics. Right now, we're this blue circle. We're the guys studying population disease genetics. We're the guys who have to drive around and find cases to study, bring them in, do molecular tests that we can afford, and then decide on the basis of that if we've made a gene discovery. But simultaneously, as we build these clinical translation efforts, the individuals are being tested and their information is going into their medical record. So those red circles are appearing, and in fact, they're getting larger and larger. And as time goes by, as each of us gets a genome sequence, whether or not we're going to have children, as a carrier test, or we have a potential malignancy, we want to test for cancer, then we'll see more and more of that data going into the record. So in the future, the medical geneticist will be studying their science, more like molecular epidemiologists. So I would say there's probably right now an idea that let's sequence the astronauts. And let's see what we can determine from those or others in the program, and use that information in whatever way we can as a predictor and as a backup for any other information correlations that might come along. But I would think that what's probably going to happen is the astronauts of the near future are already going to be sequenced. And it's not going to be by the agency, it's going to be by their local doctor because of something else, or because their family was for some completely different reason. It would be as big of a deal as saying, let's x-ray them. You might do it just so you've got the data and you've got the data in your own place, but it will be so unspecial as to be routine. And that will be defined by us as success of the genome program. So those are my comments, and I want to thank the group I've been working with actively here. I want to give a special thanks to Dr. Kasky, who was my mentor and now my colleague here in the front of the audience, and is a founder of the Human Genome Project, and really a founder of the whole field of molecular medical genetics. So it's a privilege to talk in front of you, Tom. But thank you very much for hearing my comments. Do you want to take some questions, or
Right.
to move on?
Yes. We have a few minutes for questions for Richard. And thank you very much for a really, truly outstanding and informative talk.
Excuse me. What would be the time frame for when we could, each of us individually, expect to just go to a doctor and end up with having our genome map out there?
I think that we're in the early PET scan days right now, and that we're at that equivalent point. And that, you know, pretty much I can answer yes if you're really determined, you can go and get this test. And then if you say, no, I want to know routinely in the community, then it's a question of which community and how routine. But I can see the proliferation of these methods at least as rapidly as CT scanning, or if not PET scanning. Tom, you should feel free to jump up and answer any questions too.
I was just going to add to that. In the studies that we've done with the Young Presidents Organization in Houston and their doctors.
Here's a microphone, Tom.
In the studies that we've done with young executives in Houston, the Young Presidents Organization, and their doctors that wish to be sequenced, the medical return on those studies is most positive and useful if the volunteer has an illness or there is a positive family history of an illness. The return is quite high on that. If you're disease-free, your family history is negative, the likelihood we're going to find something useful at this stage is not very high.
Okay, I have a question. Back. Related to, I mean, it's a fascinating subject and a great body of work you're presenting. So 2 questions. It has to do with, first, what is the sequencing plan associated with the mitochondrial versus, you know, primary germline nucleic DNA? And the second has to do with, we know that a number of these cancers are really not familial, maybe 10-15%. So what about the epigenetic phenomena, for instance, DNA methylation that doesn't affect the germline but produces these diseases? How are you going to get a handle on that and study it?
Well, thanks. The first one is a quick question. The mitochondrial data come right along right now. We have the assay organised so that we get the mitochondrial, and it's many times useful in pathology. But the second question about the role of epigenetics in cancer is more broad. Epigenetic phenomena are clearly involved in driving some cancers and are clearly reflective of states of cancer conditions. Today I didn't talk at all about the Cancer Project, where we've looked at a lot of the sequence of a lot of tumours to understand the DNA changes, the mutational changes, as well as the epigenetic changes. But I would say, despite the fact that epigenetic phenomena are intimately involved in tumorigenesis in all aspects, the handles on what are going on most easily come from the DNA mutational studies. Often we'll find, I don't want to get too long here, we'll find situations where a gene is clearly involved in cancer. We know that from the mutations. And then when we study it in more depth, then we see the epigenetic effectors of that gene, and we begin to understand the epigenetics. So it's important, and it's all linked together. You have time for one more? Oh, sorry.
I would like to ask, Obviously, that is the future, what you are talking about, and you may call that a parallel universe because we are here for space and space medicine, and that is your universe. The question is, as a flight surgeon, we are involved in selection of the crew, and you mentioned that you would have some genetic defects found in yourself. Do you think you could do what you have done, that you could have done your job if that would have been known before?
Well, it may turn out that I can only do I was predisposed to my job because of my genetics. I mean, I'm quite myopic too. I wear contact lenses, so I was an avid reader as a child, so I was in the academic set, even though I couldn't read the blackboard at my primary school without walking up to it. So what I mean is that maybe yes, maybe no. It's very complicated, but we will find out. How's that?
What about identifying genes with protective function?
I'm sorry,
Identifying genes with a protective function?
Well, yeah, I'm sorry I missed the radiation sensitivity discussion yesterday, but clearly the burden of radiation is high in these environments. The response to it of individuals is greatly different. There's a repertoire of genes involved in DNA repair and in soaking up oxygen radicals for which we have clear genetic heterogeneity. And so I think this is a very fertile area for investigating and really understanding the phenotype relating to different genetic signatures.
Well, thank you very much, Dr. Gibbs, for a really outstanding talk. Stimulating discussion, a lot of questions. There's now a second presentation, actually, and I invite Dr. Graham Scott to come up and introduce the next presentation. Thank you.
Thank you, Jeff. So you're in for a real treat. We've just had the first stanza with Dr. Gibbs, and it's my pleasure to introduce Dr. Kim Benstead. She's very graciously joined us here at ISMS and is going to be introducing you all to the high seas. Just a few quick words before Kim joins me up here. So Dr. Benstead is actually a physicist. She has a BSc in physics from McGill and then went on to do a PhD in artificial intelligence at the University of Edinburgh, where her thesis topic was on computational modeling. She has a very interesting background, actually. She then went to Japan and worked for Sony on human-computer interfaces, and then in 2002 joined the University of Hawaii, and she's a faculty member in the Information and Computer Sciences Department there at the University of Hawaii, where her research interests include artificial intelligence, human-computer interfaces, and long-duration human space exploration. So Kim has a really rich research program. She is actually the co-investigator at the University of Hawaii's NASA Astrobiology Institute. She's been a summer faculty fellow at Ames Research Center, where she worked on subvocal speech recognition in the neuroengineering lab. She was chief scientist on the FMARS 2007 long-duration mission. This was a 4-month Mars exploration analog at Devon Island in the Canadian High Arctic. And she's also worked with the Canadian Space Agency on their planetary analogues program. And so that brings me close to the present day, I think, where Kim has really taken on this role as the principal investigator for the high seas. And she's going to tell you much more about that, but it's a relatively new analog, and they're on their first of a trio of missions. So again, Kim, it's a real pleasure to have you here. Welcome. Please come on up, and we're really interested to hear from you.
Lovely. Thank you so much for the introduction, and from our host to our host, thank you so much for having me. It's a real honor to speak to such a prestigious group as you all. And I've really enjoyed the discussion over the past day or so. So I'm here to talk about high seas, and I did promise not to show any PowerPoint slides, but I got away with a single image of the high seas habitat. It stands at about 8,200 feet on the slopes of Mauna Loa in the saddle area between Mauna Loa and Mauna Kea on the Big Island of Hawaii. So I'd just like to back up, and many people here have analog experience, but I wanted to give a bit of a big picture of what analogs, as far as I'm concerned, are really valuable for. One, they're excellent at helping us discover problems, and some of these problems only emerge over the longer duration. Some of them only appear when you start to integrate the systems. And when I say systems, I mean engineering of systems, of course, but also human systems. When you start putting together humans and the systems that will sustain them and have them use those systems over the longer duration, new problems almost always emerge. And at this point, I have to admit that one of the hazards of analog research is most of these problems look obvious in hindsight. We have many, duh moments when we realize that two systems aren't necessarily going to work well together. The second category of successes for analogs is testing solutions to these problems, so preventative measures, countermeasures. And then finally, one that I feel is quite interesting. In computer science and software engineering, it's a principle of the field that you design in the context of use. And what I mean by that is if you're assigned, say, to produce a medical record system, you don't sit in your office and think about medical records. You go to a doctor's office and you see how paper medical records are used, who uses them, how they use them. And then in that context, you start to think about designing your systems. Now, it's hard to do that for space. We're not going to be able to send our designers to Mars before the astronauts get there, obviously. But analogs are a good way to start to expose them to some of the conditions that explorers are going to face in Mars exploration. So to go on to high seas a bit, it is an isolated and confined environment. The dome you see there is a geodesic dome. It has 2 stories on the inside, a total of about 1,000 square feet of living and working space with quarters for 6 crew members. The power systems, you can see, there's a solar array, there's also a hydrogen fuel cell, and between them, they work very well to power the habitat. The habitat is also very instrumented. We're collecting data on everything, temperatures, motion, carbon dioxide, all of the use of energy and water and other resources in the habitat. So we get to collect a lot of very interesting data. Now, like all analogs, high seas has its strengths and its weaknesses. No one analog is good for every study. And the strengths of high seas is due to the extremely steady climate at altitude in Hawaii. We only have about 5 degrees of variation over the year. We can run very long duration missions quite simply. Also, as you can see, the area around the habitat is geologically and visually very Mars-like. Geologically, it's very much like an early Mars. The lava fields are much younger, but of a very similar type you might expect to see on Mars. And this not only adds to the psychological plausibility, but it also allows the crew to do relevant field work. They go out in the field and do the kinds of geological field work that you might ask of an astronaut team. We have high latency communications. All comms are delayed by 20 minutes each way to simulate a worst case Mars situation. As you can see, it's visually very isolated. The only real signs of human activity you can see are the telescopes off in the distance on the peak of Mauna Kea. One advantage of this over some of the more serendipitous analogs, such as Antarctic, winter overs, and so on, is that we get to choose the crew, and we get to choose them specifically to meet the needs of the research we're doing. It's relatively inexpensive, certainly compared to space, but also compared to the polar missions. It's repeatable under very consistent conditions. We can run these studies one after each other and only vary the conditions that we're interested in varying. And Finally, and this relates to some of the discussions that we had yesterday, we're able to have a very high autonomy crew. This is largely a side effect of the latency in the communications, but also a deliberate design decision. And one more point is that failures at high seas have genuine consequences. A few weeks ago, their composting toilet failed on them due to not quite properly following the instructions, and then the crew had to manually clean out 2 months of 3 people's worth of human waste, which was, they're not going to do it again. They're not going to make that particular mistake again. So it has consequences, but not consequences that are going to risk the life of our crew, which means that we can push them a little bit harder and still meet IRB constraints, because if we need to, we can get them to a hospital very quickly. Okay, some of the weaknesses. Obviously, this is not Mars, and our crew are not astronauts. It is not as hazardous. It is not as remote as Mars. We have Earth gravity. The radiation is not Mars radiation. Our suits, which you'll see in a moment, they're bulky, they're awkward, they're difficult to work in, but they're not life support systems. And again, in reference to a discussion from yesterday, we do actually have 2 types. I won't say which one is the Russian equivalent and which one's the US equivalent, because I don't want to make any enemies. But we do have 2 types, so there's a certain amount of redundancy there. It's not a closed system. Our airlock is just a room that the crew wait in before going outside. And you'll see our crew, although we do try to choose crew who are as astronaut-like as possible, realistically, they're quite similar to people who apply for the astronaut program and make it into the highly qualified group. In fact, many of them have done that, and many have been interviewed. But they are not astronauts, and you'll notice that they tend to skew younger. This particular group is quite young, but that's in part because we've lost one crew member for personal reasons who was older, and he skewed the average to what we're aiming for. Also, there's the motivation issue. They're extremely motivated, but there's 2 factors that affect their motivation both positively and negatively. Negatively, they don't get to go to Mars, and obviously the physical and emotional journey of being one of the first crews to go to Mars is tremendously motivating, and they don't have that motivation, although they're very eager to contribute to the program. On the flip side, they are always aware that it's possible for them to leave, and that, of course, changes their motivation and their state slightly. And then finally, although we do give them geology training, systems training, teamwork training, they get much less training than an astronaut team would get. So a little bit on our crew selection process. We do an open call. We've got a lot of international publicity, particularly for our first mission on a previous study, which was last year. We had 700 applicants for that crew, which was very surprising to us. We expected to have to be actively recruiting people, and we didn't. Now, for good or for bad, the vast majority of those 700 were not qualified. There were only about 150 that met our basic requirements. For this mission, which is currently underway, they're about halfway through. This is the first of 3 missions focused on behavioral health and performance. The previous was a food study. We only had 150 applicants for this one, but they were almost all highly qualified. So we ended up with roughly the same pool of qualified candidates. The first stage after that of crew selection is, of course, checking their CV for education, relevant background, experience in complex operational environments, appropriate skill sets that we're looking for, generally looking for highly qualified candidates, more or less following the NASA selection criteria. Then we down select to 30 to interview. We interview them remotely. We do some psychological screening. The screening really only eliminates the extremes in terms of cognition and personality types, but it is still very valuable. Then, based on those interviews, we down select to 9, trying to balance for skill sets and demographic characteristics. You'll note that our crew involves both men and women, scientists and engineers, military, civilian backgrounds, and English as a language first speakers, people who speak English as a second language. And over those and other parameters, we try to not have anyone isolated if we can possibly. So, for example, if we're going to have both men and women, we want to have at least 2 of each. Of course, we could also have an all-male or all-female crew, but we don't want anyone isolated on any of these critical characteristics. So then these 9 interview each other pairwise, give us feedback on how well they get along with each other and how much they'd like to work with each other. And based on that, we select 6 for the crew and keep 3 in reserve. So I think our recruitment's been quite successful. We get some excellent candidates. You'll see in a moment our crew is very good. But 2 places I think we're weak. I would like to have a lot more international participation, and I'm speaking even more directly to our Russian and Japanese colleagues here. We'd love to have some participation from there. And then the other place where we're weak, sadly, is Hawaiian participation. We've had a really hard time recruiting people from the island Hawaii to apply. So it's not that there's been a quality problem, but an application problem. So we're trying to improve that. So quickly on the current research, the current projects, we've got a 4-month mission underway. We're then going to do an 8-month mission, and then we're going to do a 12-month mission. These are all funded under the NASA Human Research Program and run by the University of Hawaii. The current research team includes some names that I'm sure are familiar to you: Steve Kozlowski from MSU, Pete Roma from IBR, Wendy Bedwell from USF, Chris Miller from SIFT, and Matthias Basner, who's providing the cognition tool set. The general goal of the current research is to compare team cohesion measures and team process measures with team performance. So the trick there is to measure team performance in this analog environment. We're doing that a lot of different ways, both compliance with the study, submitting reports, doing their own research, but also the geological fieldwork. They're doing a series of geological fieldwork tasks as a team, and they're being graded on them much by a geology professor. So that's giving us our feedback there. Some other things we're looking for are some phenomena that we've seen in other long-duration missions, such as the crew-ground disconnect, which we've spoken about a little bit. That's when the crew has the perception that mission support doesn't understand what they're going through, is not providing the information they need, isn't communicating well enough. And then similarly, ground might have the perception that the crew is being overly demanding. Why won't they do this one small thing for us that we need from them? Those mutual perceptions cause real problems, and even when you anticipate them, they don't necessarily disappear. We're also looking for third quarter syndrome, and this perception from other environments that although cohesion improves performance, it might negatively affect compliance. The idea there is if you have a highly autonomous team, they will perform very well, but they might stop listening to what ground wants them to do. Is that a good thing, a bad thing? We're interested in seeing if it's a genuine connection. So very briefly, in addition to the main study, we like to have as much opportunistic research as feasible. So these are other studies, not the main funded study, that have several advantages. They allow us to get even more data, even more value out of these isolated crews. If you're going to put 6 people in a can for 12 months, you want to get as much science out of them as you can. It also provides a path to future funded studies. So all of the current studies were actually opportunistic research on our first food study. So that serves as a pilot, which we then turn into the next funded study. And then it also gives the crew realistic and meaningful work. That's very important. Over these long durations, make work isn't useful. They need to be doing meaningful work that's publishable, that has meaning to the crew themselves, and the opportunistic research provides that. So last thing before we go to a video of the crew, I was asked earlier, what research I see coming next for high seas. And based on previous discussions and some of the discussions here, I feel quite strongly that it's going to be in the area of providing psychological and medical support to long-duration crews. What do you need to provide, especially under these high autonomy conditions, to keep the crew happy and healthy over the long durations? So with that, I'm going to hand over to the crew. Let me just explain before we show this video. Because of the high latency conditions, and we weren't going to violate those, as much as it's an honor to speak to all of you, we weren't going to violate those for the purposes of this meeting. So what we've done instead is we've collected questions from you. We forwarded them to the crew. They've prepared a short video introducing themselves, about 10 minutes, introducing themselves and giving you a sense of what it's like to live at the habitat. And then they are going to, in a one-way video, answer as many of your questions as they can. So with that, let's see the video.
So we can read and take them, but we can also use our laptops. The sleep monitoring, activity tracking, and our exercise intensity. So overall, it's quite a lot of data to collect on the mission, but the crew has gotten into a rhythm of filling everything out, and it's become part of our daily routine.
Members of the right side here, do you have a patient? Nothing should be special about the way we prepare food, but all our foods are preserved, hydrated, and desiccated for preservation. Things like dehydrated foods, condensed liquids, even there's food. From this point, Amy will go and show you the exercise area.
This is our general first floor area. This is where we exercise, have meetings, and social gatherings. For workout equipment, we received a treadmill, a bicycle, a pull-up bar, resistance bands, and yoga mats. The females in the habitat do a sanity program as well as a pull-up program. We're participating in 2 exercise clothing program studies. One is from Space Tech, and the other is from JSC with the Advanced Clothing System. The crew works out between 1 and 3 hours a day, and the more we work out, the better we feel and the better we sleep at night. So next, Tip is going to give you a very quick review of our medical facilities.
As you can see here at the high seas, we're pretty well supplied. We are equipped to deal with any minor injuries or emergency situations. Over here we have our box from the World Clinic, and they provided us with a really good sample box of supplies and different medications that we can use. They also provided an instruction book that explains what to do under different circumstances, and also tells us when it's time to call a doctor for a stimulation. We have an AED, which is always important to have on hand, splinting material, bandaging material. We have anything to treat any musculoskeletal injuries, as well as being fairly well stocked with medications. We can handle anything from colds, just generic pain, digestive issues, and they also equip us with a longboard scoop stretcher, so that in case we have to go out into the field to get anybody who may have injured themselves, it's a lot easier for us to maneuver them and get them ready for emergency care. Care-wise, it's a little bit different here. Due to the 20-minute communication delay, you can't really have a telemedicine operation. So instead we do remote medicine, where we contact the doctor via email. We'll send him videos if there's something that we're particularly concerned about, and he'll video chat us back 20 minutes later. Now Lucy's going to go ahead and show you guys the lab back.
This is our scientific laboratory, and where we keep all of our equipment for our research project. And this is also where my experiment with plants growing on different wavelengths. So I'm investigating the growth of plants at a different wavelengths. I'm growing lettuce and radishes under red and blue light here, white light here, and red and blue and white light in my third treatment. This setup is these 2 lamps and the trays were led by the Kennedy Space Center. These setup was already used in the deep space habitat in the US for previous testings. The third lamp I have was a loan from Spectra, a Swedish LED lamp company specializing to growing plants. In addition to looking at the effect of plants, of wavelengths on plants, I also investigate the effect of plants on people, and the crew is always very happy to have additional fresh vegetables, lettuce and radishes, in their diet. This system is a biomass production system for education, which is made by Architect. We are using it here to investigate even further the effect of plants on the mood of the crew. I have them take care of the plants growing in there every day. They fill in a sheet and they report what they do to the plants, how long it took them. Also a way for me to look into crew time spent to take care of plants. Here we are growing a much diverse variety of plants. We have peas, we have tomatoes, we have extra radishes and lettuce. This is to have more fun in terms of additional veggies in the diet. This system is very interesting because it's the precursor of veggie, and veggie is currently on the International Space Station being tested by astronauts for the effect of additional fresh vegetables in the diet.
I'm now standing in our bathroom. It looks like a regular bathroom, but in the same way water would be limited on Mars, we are limited in water here, and we cannot take more than 8 minutes of shower per week. In order to save more water, we also have dry composting toilets. What's interesting is these dry composting toilets are similar to what a first compartment of a bioregenerative life support system would be on a future mission to Mars.
The second floor of the habitat consists of a single bathroom and 6 crew quarters. And each of the crew quarters is about 50 square feet, give or take. Inside, we have a small desk, a shelf, a stool with some storage, and a bed. And that's basically it for upstairs. Next, Tiffany's going to take you into the airlock and show you some of the EVA equipment.
Next, we're going to go ahead and show you guys the EVA prep room and airlock. Why don't you guys come along with me? Welcome to our EVA airlock. Here we simulate a 5-minute decompression time before going out on any EVA. And then upon re-entry, we simulate a 5-minute repressurization of this space right here. This is also where we prep for EVAs. So over here, I have the liquid cooling garment, the LCG, as well as its water carrying case and camel packs. The suits do tend to get pretty hot out on EVA, so it's pretty important that we keep the crew relatively cool. That way we don't have any heat stroke concerns or heat exhaustion. Behind me, you can see the MXC. That's from the University of Maryland, as well as our modified hazmat suit. We take both of those out into the field for our EVAs. And then over here we have kind of our EVA prep station. So the crew will utilize this space to get ready. On leaving for EVA, the crew members take these little packs. These are little individualized med kits with just some basic trauma, bandaging, face mask, that type of stuff. And then we also have, in case of a bigger emergency where we need to break simulation, we have a bigger med kit with more equipment ready to go. That way then either myself or whoever's back here for the EVA can quickly get us medical equipment. Now Ross is going to go ahead and take you guys outside for a little bit. Bye.
So we've suited up here, and you're standing in the airlock and you need to go outside. Before you can go outside, you have to wait 5 minutes to simulate what it would be like to have the air pressure in an airlock drop to the level of a Martian atmosphere. When 5 minutes have elapsed, you open the door and you step outside. Okay, so the 5-minute countdown is over. We're going to open the door and we're going to step outside. Follow me. It's a beautiful day on Mauna Loa. You can see Mauna Kea off in the distance there. All right, and this is our little neck of the woods. Nothing but red ground and lava flows. So we're on top of the cinder cone here, and as you can see behind me, Commander Stedman is taking some geological samples. And we've had to characterize just about everything about this feature up here. So if I continue turning around, you'll be able to see Annie and the hazmat suit behind me. And if you look on further, you can see the dome and Mauna Kea off in the distance.
Okay, now we're going to have the crew answer your questions. I think that they're ready to go. Guys in the back will summon them.
Hello, everybody at the International Space Medicine Conference. Thank you for inviting us to speak today. My name is Ross Lockwood, and the crew of the High Seas is just behind me. We're here on the slopes of Mauna Loa on a NASA downlink through the Halipaka'u Center at the top of Mauna Kea. And we've got a list of questions here that you asked yesterday, and we're going to go through them and answer them. So let's get started. The first question, and I think the most relevant to a lot of members of the audience, is, do any of us, the crew, want to become astronauts? And this is probably one of the easiest questions for us to answer. Of course, none of us would have applied to the High Seas program if we didn't have some kind of aspiration to join the astronaut corps. So maybe a goal after this is to use the High Seas program as a stepping stone for applications in our respective countries. The second question is something that all of the crew is going to answer in turn. So I'll start. The question is, what scientific experiments are you carrying out? Myself personally, I'm carrying out an experiment using 3D printed surgical instruments, and we're comparing these instruments in terms of their speed and dexterity to their stainless steel counterparts. So this may be interesting to some of you in the crowd, but we have a series of 4 different surgical tasks that we do to evaluate those things. I'm also completing my PhD in condensed matter physics, so one of my daily tasks is actually working on my thesis and running simulations for my project. Lucy's going to speak next about some of her scientific experiments and move on with some of the questions. So let's get her up.
Hello. So, as you've seen in the video, my scientific research involves growing plants in the habitat. And I'm now going to answer one of the first questions we had, which was, how are conflicts between the crew resolved? Well, in the high seas habitat, we have a very radical way of dealing with conflicts. That's I don't know if you can see, but that's one of the way we deal with them. And I'm just joking. Actually, we detect conflicts at a very early stage, and we know that the success of the mission depends on our relationship, on our good relationship. And we also know that we are in a very confined space. So we detect them very early, we diffuse them, and we move on.
Good morning. My name is Casey Stedman, and I am the mission commander. In addition to my role of managing the crew and overseeing our scientific objectives, I also work as the mission geologist, and I'm doing experiments, or at least doing research onto the proliferation and impact of social media as part of our social outreach program. Some of the questions we've been looking at here that you guys have asked has been about the conflicts, if we've had any conflicts with mission control. And I have to say that we really haven't had conflicts so much as we've had some misunderstandings. Since all of our communication is through a textual format, either by mostly through email, sometimes the tone and intent gets a little distorted, but it hasn't been enough to disrupt the mission. You asked about the key attributes that are required here, and I'd say that probably the most important one has been resourcefulness. We're almost autonomous here on the mountain in the habitat, and our ability to be patient and have a lot of ingenuity in order to accomplish our tasks has been very key. The mix of genders and scientific backgrounds adds just enough diversity of opinion and experience in order to accomplish these tasks. There's also a question about the daily routine. Things are fairly stable right now. Most of our days begin around 0700 and continue to about 2200 at night. After breakfast is followed by physical fitness, carrying out the timed events of our scientific research. After lunch is often physical fitness as well as our mission tasks. Our social gatherings include most of our meals and a recreational time after dinner. And we'll go on with Ross now.
All right. The next question is, what is it like sleeping in the high seas habitat? And are we tracking how much sleep we are receiving via some kind of fitness monitor? So, as you know in the video earlier, we all wear armbands, the SenseWear armband, and that does track our sleep, so we get a measure of that. I'm also wearing a Jawbone Up, which does it as well. And we have Zeo hardware here that we can wear on our foreheads, but that tends to disrupt the crew's sleep more than track it, so we haven't been using that hardware. The high seas habitat is actually a very quiet place up on the slopes of Mauna Loa, so sleeping here is quite different than any of us have experienced or even expected. One of the reasons that, so sleeping in the high seas habitat is similar to what you'd expect if you were actually sleeping on Mars. The only noises we really hear are the systems here in the habitat, which go into basically a low power mode at night and don't make a lot of noise, and some environmental disturbances such as wind and rain. So you maybe not expect so much rain on Mars, but that wind is ever present no matter whether you're here on the volcano or somewhere on Mars. That inside the habitat is extremely dark at night, and Annie is going to tell you a little bit more about the lighting next.
All right, the next question is there any special lighting in the habitat to wake you up, make you more alert, or put you to sleep? The habitat is equipped with standard fluorescent and LED lights. However, KSC gave me some ISS certified lights that I'll be installing before I leave. These are programmable color-changing LED lights. In the morning, there's a bluish tint, and during the day, there's a white tint, and at night, there's a red tint. So this helps monitor the crew's energy levels, alertness, and melatonin levels.
Morning, Houston. So in talking about sleep, I'm going to go ahead. We had a question about, can you take sleeping pills like Ambien or stimulants to make you more alert? And as you saw in the video, we do have quite a few medications that we're well stocked with, and we do have some over-the-counter sleep aids. Also, for more severe cases, we're able to contact our remote physician, and he can prescribe Ambien, and then I can administer that to the crew member who needs it. As for stimulants, with the exception of coffee, tea, and my favorite chocolate, we don't really have any medical stimulants. One of the other questions that we had are we sampling biofluids for downstream omic analysis or metabolite analysis? So the only fluids that we collect here in the habitat is salivary samples, and we collect that for the overarching study, which does a stress analysis. I also collect that for my own personal research, which focuses on stress and performance during EVAs. As for other fluid sampling, that's not currently occurring, but I can say after spending 2 months in the habitat here that it's a pretty good platform for this type of research, so hopefully something will pick up. I'm going to change topics a bit and focus on some of the more challenging aspects of the mission. So we had a question of what are the 3 most challenging aspects of this mission in terms of things that required us to adapt. And I'd say the 3 most, there was 2 mental and 1 more physical challenge. The first mental challenge was really adapting to a new daily routine, adapting to everything that was just different from what we had come from what we were used to. The next most challenging aspect was adapting to each other. I think this is probably more simulation and analog specific because in a real mission, you would know your crew very well before you went. But here, we all got to know each other about a week before entering the habitat and then really inside the habitat. The last challenge is more of a physical one, and that's EVAs. As you guys saw in the video, we have 2 types of suits, the hazmat and the MXC. Both are very restricting in movement, and over the challenging volcanic landscape, it can be very physically difficult to maneuver, and it required a lot of adjusting on our part. The last question I'm going to answer today is probably one of the more difficult ones, and that's what's the most stressful event that has occurred in the habitat? And one of the reasons why this is so difficult is that we really don't have any severely stressful events happen. Probably the one that comes to mind the most is that we had 1 crew member who was going through some very severe personal difficulties, and this was very stressful on that individual as well as the crew. So dealing with that was emotionally stressful. We do have daily stresses, but we're all very reactive individuals, so we tend to respond very quickly to stresses like the terrifying malfunctioning toilet or loss of power or even injuries. We respond very rapidly, and If it's a severe stress or something that's very, very difficult, we manage to come together as a crew. I'm going to go ahead and hand you off to Ross now.
All right. Thank you, Tiffany. So just to kind of lead in with what Tiffany was saying about stress, the next question is, how frustrating is the 20-minute communications delay, and how do you cope with the latency? So the 20-minute delay extends from our email to our web browsing, and for me in particular, since I'm responsible for the communication networks, it also affects troubleshooting on our end here. So this is something that is very difficult to overcome and is one of my greatest sources of stress. And the reason that is stressful is that a procedure that might take 15 minutes to communicate by voice back and forth through regular troubleshooting channels can take upwards of a day. If we're trying one thing, we're waiting the 20-minute delay for the response to even be received and another 20 minutes before something new can be passed down. So we're looking at a minimum of 40 minutes for a single troubleshooting cycle. And that could be upwards of an hour if the person on the other end or us on this end aren't checking our emails immediately. So this is one of the greatest sources of frustration. And simply our way of coping with it is to read a book or do something different while we're waiting for a response. There's always small tasks that we can add to our routine that will fill in. That 40-minute delay is really a great source of frustration for myself in particular. What the next question is one big improvement that I would make to the high seas habitat. And I think my answer to this is more backups. We have a lot of systems here that are running that are really critical for our mental health, for the health of itself, and just in general there aren't enough spare parts for us to use. So to give you an example of a good backup system, our power system has actually 3 redundant sources. During the day, our 36-panel solar array is charging a battery bank, and so during the day we can have upwards of 5 kilowatts at any given time that will run all the systems in the habitat. The battery bank is a 20 kilowatt hour system, and it will run the entire habitat through the night in the low power mode. If for any reason, such as rain and cloud, the solar panels aren't able to charge the batteries, we have a fuel cell backup that we can use in the nighttime to run our systems until the sun comes up again. If the fuel cell isn't working, we have a generator that we can turn on from within the habitat as well. So that's an example of a good backup system. The next thing I'll do is give you an example of bad backup systems. We had a failure of the treadmill early on in the mission, which prevented us from using it as our cardiovascular system. As a backup for that, we had a bicycle, and we requested the parts for the treadmill so that we could get them during crash landing resupply missions. And the day that the crash lander arrived, one of the belts inside the bicycle broke. So if we hadn't received the spare part for the treadmill, the bicycle and the treadmill would have been broken simultaneously. And at the moment, we only have the treadmill. So if something goes wrong on the treadmill, we're in the same situation as before. Okay. Since we're a little short on time, I'm going to pass the next question on to Annie. Just do the relevant ones now.
Is it? Okay. So the next couple questions are, do you think you could last more than 4 months on the mission? And could you live in the high seas habitat for the length of a Mars mission, which is 3.5 years? So 4 months, absolutely, longer than 4 months. If you have the right systems to monitor, the science to work on exercise equipment to have, and a good crew to interact with, time really does fly inside this analog. For a 3.5-year mission inside the high seas habitat, I would definitely like to see some higher fidelity systems to maximize the benefit of the scientific advancement to put humans on Mars. For example, we could have maybe a closed loop life support, some bioregenerative systems, fully sustainable energy and power, and then a lot of science that would benefit the entire community for having people in space. So we all want to positively benefit human space exploration. None of us would be here if we didn't want to do that. So I think if you had a mission that was 3.5 years inside an analog habitat and you found the right people and the right science and the right systems to develop and advance, you would have a line around the block for sure, and I'm sure you would be able to get a lot of participation. The next question is, how do you communicate with family and friends, and how does the 20-minute delay in communication affect interaction? So for any type of long-duration mission, whether it's a deployment or an actual space mission or even an analog, you have to give up your life back home. For us in the analog, we can leave at any time. However, what's the point of coming here if we're going to just come home whenever we want? So I set up a good network back home for a good support system. I was able to tell people why I was passionate, why I wanted to be here, why this was benefiting everyone. So that created a positive environment back home so that you could rest on it here. I have a private Google Plus community so I can tell friends, coworkers, and family stories and pictures of what's going on, and that seems to be going fairly well. And then in the morning and afternoons, I do a typical uplink and downlink for communication. Of course, catastrophic things can happen back home, but that's something you hope to talk about and discuss so that you can stay as in sim as possible. So hopefully those issues don't come up, but if they do, you sort of have a plan B on how you can stay in sim and how to deal with that as a crew. And now I'm going to pass it over to Casey.
Hi, you asked about what we do for recreation and relaxation. A lot of the crew is, we're all voracious readers, and as a crew we've enjoyed playing games in the evenings and watching a lot of new films. I think I'll pass this on to Lucy now.
Okay, one of the other questions we had was about if the experience was what we expected and what we have learned so far during this mission. So for most of us, it's been exactly what we were expecting, even though we were expecting something maybe more in a rigid frame with more rules. We were not expecting to cope so well with isolation. All of us is doing really well. We've learned so far that we still have a lot to learn before we can actually go on a real mission to Mars. And the last question was, what are we going to do as soon as we get out of the habitat? I think I can talk for all my crewmates here. We'll spend probably a couple of weeks eating only fresh fruits and vegetables and lay in the sun. Thank you.
That's it as far as the downlink session goes. So we'd like to thank you for letting us join you at the conference today, and we hope that we have an opportunity in the future to interact with you without the delay. So back to you, Kim.
So there you go. That's our High Seas crew, and I'm very proud of them. I think they're excellent analog astronauts. And if there's one or two more questions, if there's anything left out or that was spurred by their responses, I can answer one or two questions now. Yes?
Your pamphlet mentioned need for personnel in the future. Could you expand explicitly on, you listed undergraduate as well as graduate student involvement. Now, many of these individuals are graduate students, but can you expand on that a bit, what you see for the future?
Well, we're looking for undergraduate, graduate, and postdoc researchers outside of the habitat to help with the research team. But also, this group, they're mostly graduate students. Our previous crew is actually late 30s, early 40s mostly. So the relative youth of this group is two crews, not an aberration, but a difference. But yes, graduate students, postdocs, recent graduates, actually people of all ages have applied. Grad students tend to be quite good because they can take 4 months out of their lives without too much damage. Any other questions? Oh, there was one question that the crew didn't answer about what they get paid. It's not much. They get $5,000 for the 4 months and room and board. All right, well, thank you all very much for your attention.
Thanks, Kim, and that was a great lead into the next session, so terrific. Really appreciate it.